Let's continue for the controller design, okay? So start from now, we will discuss controller design. How you, given the nonlinear dynamic system, how you can design the controllers according to different conditions, like unknown parameters or with disturbances. So the first one is feedback linearization, okay? And second one is high gain controllers. And as I mentioned from previous week, that the A here is assumed to be a non-constant, okay, which implies you have the exact model knowledge, okay. You know what the inertia is, what the viscosity of the system is, if any, and okay. With the knowledge, with the model knowledge, it's easier to design the controller U, okay. And this is the open loop dynamics, where you don't apply any control input, right? So if it's zero, and this is the dynamics, which is unstable. And after you apply a control input, you design a controller and substitute into the system, you got this closed loop dynamics, okay, which is stable. And this is the objective of designing the controller that stabilizes the system, and which might originally be not stable, okay, be unstable. So the controller for the previous slide is, it consists of two components, right? One is, this first component is to cancel out this nonlinear term in the dynamics. And it this one can be canceled out because A is known, right? Because remember this, everything in your controller have to be known. Otherwise, how can you implement the controller, right? 你懂吗? Everything in the controller have to be known, okay? So everything on the right-hand side have to be known. So your state have to be measurable. Your system parameter have to be known. Otherwise, you cannot implement the controller, okay? 能懂吗? Remember this. Keep this in your mind, okay? And because we know the model knowledge, so we can design this controller. And this component cancel out the nonlinear term in the dynamics. That gives you this closed loop dynamics, which is linear and stable. Okay. So now let's prove this. Is this system, this closed loop system is stable? Or what's the stability of this closed loop system? Okay. So we can prove by using the above function approaches. You select the above function, okay, a quadratic form. And when you take the time derivative, right, and then you can substitute your closed loop dynamics from here. Okay, 听懂吗? And the result is NSD, right? Here you have x squared and here's minus x squared. So it's PD and ND. So the conclusion and is RU, right? So it's globally asymptotically stable. Okay. 能懂吗? So it's easy, right? And can you further discuss the convergence rate? Okay. So here what I did is I took this, okay, which is this, okay, and we can find the relation between x and v, right? The relation between x and v is this, right? So you replace this x squared by 2v, Then this becomes a linear ODE, and you can solve for the solution if the initial condition is known. Okay. So what's the benefit of solving this? Well, it's easier to see that it's globally exponentially stable, right? Because V, given some initial condition, okay, this V decays exponentially fast, right? And if V decay exponentially fast, so did X, right? 能懂吗 ？OK， 这样有没有问题？这边有问题吗？居民有问题吗 ？OK， so OK。So the defect is it requires model knowledge. Okay, it requires model knowledge. So second example. Second example is now we add another term, another nonlinear terms. Okay, another nonlinear terms. And again, we follow the same procedure for feedback linearization controllers. So as you added this in the dynamics, you want to add the same term with a different sign, right, in your controller as to cancel out this in the open loop dynamics. So again, the closed loop, after you substitute this into the open loop dynamics, you can get the closed loop error system here, right? And again, it's stable. It's globally exponentially stable, right? Okay. Any question? No. So let's discuss this. What's the defect of feedback linearization controllers? Other than it requires model knowledge, okay, the good terms will be cancelled. What is good terms? This is good terms. Okay, why? You know why? Okay, let me try this. Okay, and V dot is X. So if you substitute the open loop dynamics, okay, this is open loop dynamics. And closed loop dynamics. Okay, V equal to, okay, so why do I call it good terms? The reason is when you substitute the open loop dynamics into here, okay? Let's take a step back. So which is ax squared minus x cubic plus u, right? And you expand out the whole equation. You got ax cubic minus x power to the fourth minus xu. Okay, this is V dot, right? So the contribution of x minus x3 basically is it comes to minus x power to the fourth, right? So this term is always negative, right? 对不对? It's always negative. So this term can help V dot to be more negative, right? No matter what x is, right? 对不对? So if you put minus if you keep this term, okay, if you keep this term, V will converge faster, okay? But when you cancel out, so when you, and in the controllers, we design this term to cancel out this term, which is a good term, right? And that, so that the convergence rate of V dot is compromised, okay? It becomes lower. So if the controller is compensate a wrong term, okay? So it's better to keep this term. It's better to keep this term. Okay, so let's try this. Now we refine the controllers. From u equal to minus ax squared plus x cubic minus x to u equal to minus ax squared minus x. Okay, so we don't want to cancel out this, so I just kick this term out of the controller. Okay, so if I substitute this into the controller, into the open loop dynamics, what will it be? What will the stability analysis look like? So let's try. So if you sub this back to the open loop dynamics, that gives you what? Closed loop dynamics. The new closed loop dynamics becomes what? X dot equal to a squared minus x cubic plus minus ax squared minus x, right? And these terms cancels out. That give you, right? So this term have been recovered, okay? So let's try substitute this into the V dot. So V dot is x dot, okay, which is x, and substitute the closed loop dynamics into here, which give you, right? Okay. So compare with this term. Now we recover this term, okay? So it's still negative definitely, right? For sure, right? Right. But it even converge faster than this, okay? 听懂吗? And compare with the controllers, okay? Compare this controller and this. If you now say x equal to 1, okay? Initial condition. If you start from the state that equal to 1, and let's try to substitute this into the two controllers, okay? So the one on the left hand side give you what? Minus a1, okay, 1 squared plus x 3 minus 1, okay? And the one on the right is what? Minus a1 squared minus 1. So maybe let's try 2, okay? Try 2. So it's 2. And say a is 1, okay? A is 1. So what's this? It's 2. It's minus 6, 2, okay? So it's not a good example. Maybe try minus 2. Let's try minus 2. Try minus 2. So it's minus 2. And this is minus 8. Okay. So what's this? It's 8. 10 minus 14. Okay. Minus 2. So it's plus 2. Minus 2. Okay. So compare this. See? Given the same state, this is the control output. This is the control output. Which one is larger? In terms of magnitude, this one is much larger, right? Magnitude. Okay. So it requires more power, right? If the control system is a robot arm, right? The control means the voltage, right? The voltage to the motor the requirement is larger, okay, to drive or to stabilize the system, given this controller, right? So it requires more power, okay, more powerful controllers, but this one is not, okay. And that's the drawback of feedback linearization. Or maybe you can avoid this situation by observation, okay. If you see it's good terms, then you just keep it. You just keep it, okay? You don't want to cancel it out. So in conclusion, design procedure is this. Given a system structure, x star equal to ax plus b gamma x. Gamma could be some nonlinear function, okay? Gamma x could be like s cubic, okay? So the controller design is you design u equal to alpha x. Okay, so this the alpha x in u will cancel this out, and the other term, this one, will multiply with this, which is the inverse of gamma, right? This is the inverse of this gamma, so it becomes 1. So the closed loop system will become kind of like a linear system, okay? And since it's kind of like a linear system, you can design this new controller by another linear approaches like pole placement. Okay, 能懂吗? So remember, cancel some nonlinear term from open loop dynamics, and add some linear term here. Not necessary to be linear, okay? But the closed loop system could be linear, okay? And everything here had to be known. You had to know what is alpha, what is gamma function, okay? You have to know what is gamma, what is alpha in the open loop dynamics. Otherwise, you cannot apply this approach. So since it's the first controller that we introduced, for sure, it's probably the most simple controller design, okay? So the next one is, how about consider the unknown system parameters? A is assumed to be unknown, okay? In the previous case, it had to be known. What if A is unknown? Okay, then you have two options. Option one is you design high gain controllers, and it's also called robust control. Or option two is adaptive control. You don't know the system parameter, but you put the estimate of this unknown constant in your controllers, somehow stabilize system. And the stability can be concluded as asymptotically stable, okay? So we will discuss option two, the adaptive control, later. We focus on the high gain control now. So what is high gain control? So I give an example. So given this dynamic system, okay, x star equal to theta, which is a unknown constant, sine square t plus plus u. So theta is some unknown parameter, which is which is a constant. Like in the previous case, so for example, theta is the mass of a system. Okay, we don't know the inertia of the system. What is known is its upper bound. Okay, theta can be a positive constant, negative constant, but no matter what, we know its upper bound, which is upper bounded by c. And you can design some robust controller. Okay, here the structure is minus kx. This is linear, but this is the robust controller. The design procedure will be backwards. We first follow the stability analysis and see how you can design this VR, this robust control, from the analysis. Okay, so we'll go back later to redefine this VR. So we take this open loop dynamics into analysis. Okay, we take this dynamics into analysis. We design this variable function and take the time derivative, and in which you can substitute your open loop dynamics. You substitute the controller here. Okay, minus kx plus VR. VR is still to be designed. Okay, so if you design VR as minus k2x and you substitute minus k2x, you got this, and you expand this out. Okay, minus kx and x, so it's minus kx squared and minus k2x squared, and this term. So basically, for now, this robust term is similar to this. It's minus kx, and this is minus k2x. Okay, so it's basically it's similar, but the selection of k2 will be different. There's a trick here. Here's the equal, right? Equal sign here, but here is upper bound. Okay, what happens? How can you modify equality to an inequality? Do you see the difference? So this term and this term remains the same from previous one, right? Here and here, right? What is difference is this. And is that true? Can you upper bound, use this term to upper bound this term? Can you? Anything wrong with this procedure? You upper bound. So here what I did is I upper bound this term to this term, right? This term is upper bound by this term. If you can find a counterexample, which means you agree with this result, right? So so this procedure is correct. Okay, why? Why I need to upper bound this? So think about this. This is state, right? State. Do you know what's the value of state? We don't know. We don't know the trajectory. We don't know the solution. So given this, we don't know the solution of x, right? So we cannot guarantee what x will be. And if x is always positive or is always negative, it's hard to say, right? But here is always positive, right? It's always positive. But here could be positive or negative. So it's hard, but our objective here is to ensure V will be negative, right? V will be upper bound by some V to be negative definite, which means the right hand side of the inequality had to be negative, right? But here the problem is this term, the product can be sometimes positive, sometimes negative, right? Okay. But we want it to be negative, but it's impossible because it could be positive or negative. You cannot predict what the state will be unless you know the solution, right? But it's nonlinear dynamics. You don't know the solution. So you need to consider the worst case. Worst case. Worst case means what is the largest value of this, right? You want it to be negative. So worst case is what is the largest value of this? Okay. So therefore so let's find the range of this. So you can say for A and B are any real numbers, could be positive or negative. You can upper bound this by A, B as the value of A, B, right? It's always true, right? 对不对？是吧？ Okay. Because the range of AB is this, And the worst case is this, right? This is the worst case. Okay. So that's here, this term, the last term is the worst case of this product can be. Okay? 能懂吗? So everything here had to be worst case. That's why it converts equality to inequality. This can be further upper bound by this, right? 对不对？没问题吧？ This can be further upper bound by a, b, absolute value a times absolute value of b. And the worst case of this term, this product, will be cx, absolute value of x, right? C is a positive constant, right? Which upper bound this. Any correction from here to here. So sine square is always go from step by step, right? And this, the worst case of this is 1, right? This is remains the same. C, where is C? Oh, this is theta. Theta here. So theta here, right? And theta here. And theta here. Okay? And using the condition that we know theta, we don't know whether theta is positive or negative, but it can be upper bound by some constant, positive constant c. So now you can substitute c into here, so it's cx as the value of x. Okay? Right? Make sure you understand the every inequality here. Okay? This is the upper bound of this and this. So now you have this form. Okay? So next we combine this. We combine these two terms, marked in red. Okay, we combine these two terms. So you move x absolute value of x out of the bracket. Okay, and now as long as, so it's always positive, right? So as long as everything in the bracket is positive, this whole term is negative, right? And we can drop out the terms. 懂吗? So if everything in the bracket is positive, the second term will be negative. Then you can drop out, right? A negative value can be upper bound by 0, which means we can drop it out. Okay, so it becomes beta equal to, will be upper bounded by minus kx squared. Okay, beta upper bound minus kx squared if this term is positive, if this is greater than c. Okay. 能懂吗? 有没有问题? So from here is globally uniformly stable because why? Because you won't converge to 0, right? When you see this, you cannot say it's negative definite because as x trying to converge to 0, when x trying to converge to 0, this term will be 0, right? But it's a constant here, it's a positive constant. So eventually this term will go from positive to negative. And the second term will go from negative to positive. Right. And the intersection will be where x equal to, so beta will be upper bound by some negative definite function if this is satisfied, right? But when x is equal to, you move this to the right, k2c. When x, absolute value of x is equal to this constant, this will become 0, right? And it no longer holds. 这个成立只有在这个条件下成立的时候嘛，那这个不会 一直成立嘛。When x 变成是这个 value, x could decrease from some initial condition, right? And decrease to 0, trying to decrease to 0. So when it getting smaller and smaller, probably at these values, this condition never holds, right? 懂吗？ And this condition breaks, okay? And that's why it's globally EUB, okay? It will eventually be bounded. It cannot converge to 0 because of this term. Maybe you can think it another way. What if x equal to 0? What if the objective is to prove x converge to 0, right? What if x equal to 0? This is 0, right? This is 0. Or if x is a very small value close to 0, so it's almost 0 here, right? And so the everything in the bracket is like a minus c, is a negative value, right? And this is positive. So negative, positive, and negative. So this second term is positive, right? It's positive. And the first term is almost 0 because x is around 0. So the whole term is positive. V dot is positive. What happens when V dot is positive? It's not convergent, right? So it never converges to 0. X never converges to 0. 这样懂吗? So it's like so if you plot this, basically when you start from V0, where x start from 0 and it goes to 0, but it never reaches 0 because of the uncertainty, because of the second term. So eventually it reach to some UUB. Okay. Okay, 这样没有问题。Okay, it cannot be 0, otherwise V dot will be positive. 用来让它是 negative definite 啊。So this term, the objective to keep this term is to make sure V dot is upper bound by some negative definite, right? And in which case we can say V dot is negative. That's only true when the second term is also negative. If second term is positive, it over-dominates the first term, and the overall product is positive. 我们想要右边的东西都是负的嘛，因为 V dot 要负的嘛，对 ，V dot we want V dot to be upper bounded by some negative value, right? So first term is negative value, okay, but this term can be positive, and once it goes positive, V dot is no longer decreasing. V is no longer decreasing, right? So the problem is this term, the second term, can be positive, but when, at which x it will goes positive, that's at this x. 能懂吗? This x, when this summation is 0, okay, 懂吗? 当你括号里面是0的时候，或是当你括号里面是0，就我们要让括号里面是大于0嘛，但是随着 x 变小，它就会跟着变小嘛，对不对？我们要括号里面是正的嘛，因为正格跟正相乘，前面一个负号，整个就会是负的嘛。OK， 所以我要括号里面是正的，但是 x 会慢慢变小啊，小到最后它就变成是负的啦。对不对？所以那个交叉点就是在 x 是这个值的时候，能懂吗 ？So when absolute value of x equal to this, that's the time that v start to decrease. OK， 虽然它前面还有这个嘛，但是 worst case 是这样。Or you can merge. You can merge these two terms. Okay. 你可以 merge 也可以啦。You can merge k plus k x squared. So we want this to be negative definite, right? Want this to be negative definite, but it's not always negative definite. For example, when k plus k2x squared can this be 0? It can, right? Then when x norm is 消掉一个 c when x equal to ck when x absolute value of x equal to this value, this becomes 0. So which means it stop decreasing, v start decreasing. But x is not, haven't reached to 0, right? It's not equal to 0. So before it goes to 0, v start decreasing, which means it's UUB. Okay, 能懂吗? If you substitute x into here, that will be 0. Why it doesn't converge to 0? Because of the uncertainties. Because of c, because of this c, okay? Because of this c. If c is 0, if you observe c is 0, then this will be 0, right? So it will converge to x, the absolute value of x will be 0, and v dot will be 0, which means it converges to the origin, right? But because c is non-zero, it comes from the uncertainties, okay? So if you have uncertainty in your dynamics, and you use high-gain controllers, then it won't be globally asymptotically stable. If you don't have unknown in your system, how can you control something unknown to be asymptotically stable?